Have you ever wondered why ice melts on a warm day, but a puddle of water doesn't spontaneously freeze into solid ice cubes under the blazing sun? Or why certain chemical reactions just happen completely on their own, while others need a massive kickstart of energy to even get going? Well, let's dive right into this explainer because today we're pulling back the curtain on the fundamental rules that govern exactly how and why our physical world behaves the way it does. We are cracking the hidden drivers of chemical reactions, entropy and Gibbs Free Energy. So, here's our game plan for this explainer. We're going to cover what entropy actually is, how to spot entropy changes in the wild, the missing puzzle piece of reactions, Gibbs Free Energy, and finally, some top-tier strategies for acing your chemistry exams.
All right, let's kick things off with Section 1, What is entropy? The measure of disorder.
Now, you might hear the word entropy and immediately just think of chaos, but it isn't just chaos. It's actually a precisely measurable value of dispersion in a system. When we say disorder, what we're really talking about is how spread out the energy and the particles are. Nature, by its very default, loves a mess. It strongly prefers states where energy is dispersed rather than tightly concentrated. And because we're scientists, we don't just call it a mess, right? We give it a symbol, capital S, and we measure it in joules per Kelvin per mole.
Think about it this way. Chemicals behave almost exactly like students in a classroom. Picture a highly ordered classroom. Everyone is sitting perfectly in their assigned seats, facing forward in neat little rows. There are honestly very few possible ways to arrange this exact setup. That is a state of low entropy. But then the bell rings. Students stand up, mingle, move around randomly, form groups, scatter across the whole room. Suddenly, you have thousands of possible arrangements. That right there, that's high entropy. Chemical systems naturally want to move from those ordered, rigid rows into completely randomized mingling.
So the absolutely crucial takeaway here is that entropy increases continuously as particles gain more freedom to move. Think about a solid state like ice. The particles are locked in place, just sort of vibrating, very low entropy. But if you melt that into a liquid, like water, the particles can now slide past one another, so entropy goes up. Now boil that water into steam, a gas, and those particles are flying freely in all directions with massive amounts of space between them. The entropy absolutely skyrockets. The rule of thumb is super simple. Moving from solid to liquid to gas equals a massive increase in entropy.
Which leads us perfectly into Section 2, Spotting entropy changes, or predicting the flow. Okay, here's a massive shortcut for you. If you ever see a reaction that produces more moles of gas, say solid calcium carbonate breaking down into solid calcium oxide and carbon dioxide gas, you instantly know that entropy is increasing. Why? Because you just went from 0 gas molecules on the left side of the equation to 1 whole gas molecule on the right. Gases have so much more freedom and randomness than solids or liquids. So anytime you're staring at a chemical equation, just count your gas molecules. If that number goes up from reactants to products, your entropy change, your delta S, is for sure going to be positive.
But, we can't just guess forever. We got to calculate. When you're asked to calculate the standard entropy change from a data table, just take a breath and follow these 3 sequential steps. First, add up all the standard entropy values for your products. Second, do the exact same thing for your reactants. And hey, do not forget to multiply those values by the big numbers, the stoichiometric coefficients, in front of the molecules in your balanced equation. Finally, step 3, subtract the reactants total from the products total, products minus reactants. Seriously, don't rush the math here. It's a simple subtraction, but it is incredibly easy to get backwards if you're not paying close attention.
Now let's move into Section 3, the missing puzzle piece, why enthalpy isn't enough. I want you to really think about this question. For the longest time, chemists thought that if a reaction released heat, if it was exothermic with a negative enthalpy change, it would naturally just happen on its own. But wait a second, ice melting actually absorbs heat from its surroundings. It's an endothermic process. Yet, as we all know, it happens naturally on a warm day. Why? Well, this proves that relying purely on enthalpy or just heat is fundamentally flawed. We clearly need another factor to explain why reactions happen naturally. Enthalpy just isn't enough on its own. We have to factor in the messiness. We need entropy. And that realization brings us to Section 4, Gibbs Free Energy, the ultimate chemical truth. This equation right here is the ultimate solution. It proves that both enthalpy and entropy are actually working in tandem to dictate the spontaneity of a system. Delta G equals delta H minus T delta S.
I know, it looks a bit like alphabet soup, but it's actually a beautifully balanced scale. On one side, you've got the heat change of the reaction, delta H. On the other side, you have the disorder change, delta S, multiplied by the temperature, T. This single, elegant equation tells us whether a reaction will happen completely on its own, which we call spontaneous, or if it's going to need a constant push of external energy.
Okay, listen up, because this is absolutely crucial. There is a trap here that literally catches thousands of students every single year. The number 1,000. You must divide your standard entropy value by 1,000 to convert it from joules to kilojoules before it ever even touches the Gibbs equation. Why? Well, your enthalpy, delta H, is almost always given in kilojoules per mole, but your entropy, delta S, is given in standard joules. If you don't convert that entropy by dividing it by 1,000, you are mixing apples and oranges, and your final answer is going to be completely wrong. Once you've safely calculated your final delta G value, interpreting it is remarkably straightforward. A negative result, meaning delta G is less than 0, means the reaction just goes ahead all on its own. It's spontaneous. If delta G is positive, greater than 0, the reaction is non-spontaneous. It's stubborn, and it won't happen unless you force it by continuously pumping in energy. And if by some absolute miracle delta G is exactly 0, then the whole shebang is at perfect equilibrium, perfectly balanced between reactants and products. Now, this neatly organized table maps out the 4 possible temperature cases, and honestly, it's a fantastic cheat sheet. Let's look at the extremes real quick. Case 1. If a reaction releases heat, negative delta H, and gets messier, positive delta S, that's the dream scenario. It will always be spontaneous no matter the temperature. Case 2 is a total nightmare. It absorbs heat and gets more ordered. That is never going to be spontaneous. But cases 3 and 4, that's where temperature really pulls the strings. Notice how high temperatures strongly favor reactions with a positive entropy change, because T is multiplying delta S in our equation, cranking up the heat literally amplifies the importance of entropy.
Let's wrap things up with Section 5, Acing Your Chemistry Exam, Strategies and Pitfalls.
Please, do not fall victim to these classic pitfalls. We've talked about a few already, right? Forgetting to multiply your data table values by the big numbers in the balanced equation will totally sink your score. Accidentally doing reactants minus products will give you the exact opposite sign of what you need. But especially, watch out for the trap of forgetting to convert your temperature from Celsius into Kelvin. The Gibbs equation demands absolute temperature. Always add 273 to your Celsius value. And, as we just learned, never assume a reaction happens just because it's exothermic. Always check the Gibbs.
If you want to guarantee full marks, especially on the Edexcel syllabus, stick to these top tips. When a question asks you to predict the sign of an entropy change, your very first move should be looking at the states of matter. Count those gas molecules. It's the fastest way to the right answer. Also, when they ask you to define or explain an increase in entropy, examiners are literally hunting for very specific keywords. You need to use the exact phrase particle arrangement and randomness in your written explanations. Just saying it gets more disordered isn't always enough to secure the point. You've got to show them you truly understand that the particles have more possible arrangements. So, you now hold the keys to chemical spontaneity. You know exactly why things happen. But before we go, I want to zoom out from the beaker and look at the cosmos for just a second. The laws of thermodynamics actually state that the overall entropy of the universe is always increasing. It is constantly driving toward maximum disorder, maximum randomness, maximum dispersal of energy. It's a really profound thought to end on, leaving you to ponder how these tiny microscopic rules of spontaneity actually shape the grandest scales of reality itself. Will the universe eventually reach a state of maximum entropy where no more spontaneous reactions can ever occur? That is the true beauty of chemistry. It starts with a simple equation on a whiteboard and ends with the ultimate fate of the universe. Thanks for learning with me today on this explainer, and I'll catch you in the next one.